On April 13, the atmospheric column above the central United States contained roughly 2.4 trillion megajoules of trapped thermal energy, but the staggering heat index near the surface isn't the part that has forecasters alarmed. It is the violent, structural collision between that stagnant moisture and the shearing force of the jet stream acting as a spark. Are we watching a temporary seasonal glitch, or the terrifying new physics of our atmosphere? That is not a theoretical abstraction. That is a measurable physical payload of kinetic energy hanging directly above millions of people. Over a relentless 5-day sequence, this invisible reservoir of heat would synchronize with upper-level atmospheric triggers to detonate across a massive geographical footprint. Not metaphorically, not as a headline exaggeration. Something physical. It would systematically dismantle infrastructure, suspend grapefruit-sized ice in mid-air, and violently rewrite the baselines of early-season severe weather. If this kind of meteorological forensic analysis has you hooked, subscribe to the channel. Let's look at the data. To the naked eye, on the morning of April 13, the skies over the Central Plains appeared deceptively benign. The sun warmed the soil. The winds were a steady, humid breeze drifting out of the south. But invisible to human perception, an architectural atmospheric anomaly was assembling itself across the heart of the continent. The atmosphere was not merely warming, it was loading. Over the preceding 48 hours, a persistent low-level jet stream had acted as an industrial-scale conveyor belt, actively dredging rich, saturated air from the Gulf of Mexico and transporting it northward into the plains. This was not a standard seasonal moisture return. This was an anomalous pooling of latent heat. Latent heat is the energy absorbed by water when it evaporates into vapor. It is thermal potential waiting to be unleashed. When that water vapor is forced upward into the colder, thinner air of the troposphere, it condenses back into liquid. When it does, it releases all of that stored solar energy back into the surrounding environment as pure, explosive heat. The plains were submerged in it. Meteorologists measured this volatile fuel using a metric called convective available potential energy, or CAPE. You can think of CAPE simply as the tension on a catapult. On a typical stormy spring afternoon, a CAPE value of 1,000 joules per kilogram is sufficient to generate robust thunderstorms. On April 13, weather balloons launched into the Midwestern sky began returning telemetry data that was deeply sobering. The atmosphere was returning CAPE values in excess of 3,000 joules per kilogram. The catapult was pulled back to its absolute mechanical limit, yet the sky remained quiet. This is due to a secondary meteorological mechanism known as convective inhibition, or the CAP. The CAP is a thin, invisible layer of abnormally warm air sitting a few thousand feet above the ground. It acts as a heavy lid on a boiling pressure cooker. It actively suppresses the humid, volatile air at the surface, preventing it from rising. As the morning progressed, the sun continued to heat the ground, building more and more pressure beneath that lid. The air at the surface wanted to rise, but the structural inversion of the cap held it down, forcing the kinetic potential to compress, to pool, and to magnify. It was a standoff. The physics of the atmosphere dictate that this equilibrium cannot hold forever. When the cap finally breaks, the resulting release is not a gradual transition. The air does not gently rise, it violently erupts. The stored latent heat is instantly converted into vertical kinetic energy. The atmosphere essentially short-circuits, rushing the trapped surface air upward into the freezing upper levels of the troposphere at highway speeds. All this powder keg required was a spark. That spark arrived in the form of a mid-level shortwave trough, a ripple of fast-moving, deeply cold air in the jet stream tearing across the Rocky Mountains and bleeding into the plains. As this cold air rode directly over the sweltering, capped moisture below, the lid catastrophically shattered. The kinetic initiation had begun. The atmosphere was no longer waiting, it was detonating. The mathematics of the atmosphere do not care about the calendar. In the upper Midwest, April is typically a transition month, a period where lingering cold slowly yields to spring warmth. Strong, violent tornadoes are a statistical rarity this early in the year, but on April 14, the rules were aggressively suspended. To build an EF3 tornado, the atmosphere must construct a precision machine. A mesocyclone, the deep, constantly rotating updraft of a supercell thunderstorm, is an atmospheric engine block. On that Tuesday afternoon, as supercells blossomed over northeast Iowa and tracked into southwest Wisconsin, one specific engine began to consolidate with terrifying efficiency. The sheer heat and moisture available at the surface were elevated, but not at the astronomical levels typically required for massive tornadoes. However, the storm compensated. It utilized immense vertical wind shear. Wind shear is not just a sudden gust. It is a violent tearing motion where winds at different altitudes blow at differing speeds and from opposing directions, creating an invisible horizontal rolling tube of air. The storm's massive updraft grabbed this rolling horizontal energy and violently tilted it vertical. It took a rolling cylinder and stood it on end. Between 5:33 p.m. and 5:52 p.m. Central Daylight Time, this structural anomaly dropped from the cloud base near Hillsborough in Vernon County. It did not merely touch the Earth, it ground into it. For 19 uninterrupted minutes, the vortex tracked 8.78 miles northeast across rural Vernon and Juneau counties. As it approached Reyes Road near the town of Union Center, the rotational velocity tightened, dropping the pressure core and accelerating the wind field to a peak of 140 miles per hour. The track was methodical. The damage was structural. The efficiency was terrifying. Family homes were torn apart. Numerous outbuildings were completely obliterated. Century-old trees were cleanly snapped and stripped of their branches. The exact micro-scale trigger that allowed this specific mesocyclone to achieve such rapid, violent EF3 maturity in an early season environment characterized by lower instability is still a subject of ongoing meteorological debate. The data is clear on the path. The survey is clear on the 140 miles per hour wind speeds. But the precise atmospheric catalyst that turned a typical spring storm into a localized, destructive anomaly remains genuinely unknown. What is known is that this was only a preview. The atmosphere was proving its mechanical capability on a localized scale before moving on to a much larger target. In the strict bureaucratic lexicon of the National Weather Service, language is deployed with extreme, measured precision. A standard watch indicates that the atmospheric ingredients for severe weather are loosely present across a regional area. A standard warning means a vortex has been explicitly detected by Doppler radar or a confirmed human spotter. But a particularly dangerous situation, a PDS, is an entirely different operational categorization. It is not a standard forecast model, it is an atmospheric death warrant. The PDS designation is an incredibly rare modifier. Statistically, it is appended to less than 3% of all severe weather alerts issued in the United States. Originating from the Storm Prediction Center in the late 1990s, it was designed to solve a fatal problem in meteorological communication: how to alert a population when the atmosphere transitions from a routine severe weather threat into an environment capable of structural annihilation. The PDS is activated only when the meteorological data leaves zero margin for doubt. It is not triggered by a single severe storm. It is triggered by the mathematical certainty of a widespread, systemic atmospheric collapse. To authorize a PDS, meteorologists must observe a highly specific, terrifying alignment of data. They evaluate a metric known as the Significant Tornado Parameter, or STP. The STP is a composite index, an overarching score of atmospheric volatility calculated by mathematically compounding the available thermal energy, the low-level moisture, and the rotational wind shear into a single, localized number. On a typical severe weather day in the plains, an STP value of 1.0 or 2.0 is sufficient to warrant close monitoring by forecast officers. When the STP value sharply exceeds 6.0 across a highly populated corridor, the environment crosses a critical, non-linear threshold. The algorithms stop predicting isolated storms. They predict continuous destruction. The data demands action, but the STP is only the foundational layer. To issue the PDS, forecasters must also identify extreme potential in the storm's rotational velocity, or vert. This metric specifically measures the speed at which the mesocyclone, the rotating, engine-like heart of the thunderstorm, is spinning horizontally before it ever touches the ground. Standard tornadoes might form when rotational velocities hover around a manageable 40 knots. In a PDS environment, the background wind shear is so intense that any storm that forms will rapidly achieve a vrot exceeding 70 knots. At that immense rotational speed, the mesocyclone ceases to be a mere column of spinning air and instead acts as a massive atmospheric drill bit. When the primary updraft of a supercell becomes perfectly synchronized with extreme low-level wind shear, the storm stops relying on random, localized thermal fluctuations and instead locks directly into the massive synoptic-scale energy grid of the jet stream overhead. It becomes self-sustaining. The threat is long-track. The damage is catastrophic. The window closes when a PDS alert is formally transmitted. It deliberately overrides the normal programming of emergency broadcast systems. It is an explicit message to emergency managers, first responders, and the public that standard structural sheltering, like an interior hallway or a bathtub, may be fundamentally inadequate against the incoming kinetic forces. A PDS requires the atmosphere to demonstrate the undeniable capability of producing multiple long-lived EF3, EF4, or EF5 tornadoes. These are vortices explicitly capable of sweeping a foundation clean. The issuance of this alert removes all hedging from the science. It strips away the comforting, probabilistic qualifiers of might be or could potentially. It is a blunt, declarative recognition that the atmosphere has bypassed localized instability and achieved a state of hyper-organized violence. On the afternoon, the upper Midwest outbreak commenced. The telemetric data was glaring. The low-level jet stream was screaming. The surface instability was locked. The atmosphere was explicitly advertising its intent. At 7:23 p.m. Central Daylight Time on April 13, the atmospheric physics problem stopped being theoretical. It became structural. A supercell tracking through east-central Kansas had spent the afternoon converting extreme atmospheric instability into a localized rotating engine. As it approached Franklin County, the mesocyclone tightened. The base of the cloud descended. A few miles west of the city limits of Ottawa, Kansas, the invisible horizontal rotation was finally wrenched completely vertical. It connected with the soil. The resulting vortex was an EF2 tornado. But the categorization of EF2, representing winds between 111 and 135 miles per hour, often masks the terrifying reality of what those velocities actually do to the built environment. The Ottawa tornado was not a swirling, dusty funnel skipping lightly over the prairie. It was a grounded, rain-wrapped kinetic mass. A rain-wrapped tornado is an optical nightmare. As the vortex spins, it actively inhales the heavy precipitation core of the parent supercell, weaving millions of gallons of falling water into its outer circulation. To a spotter or a resident looking out a window, the tornado is entirely invisible. It does not look like a funnel. It looks like a solid, advancing wall of black water descending from the sky. The storm did not drift. It tracked. For exactly 25 minutes, the vortex cut a 7.3-mile continuous path with the deliberate terrain-agnostic precision of a guided mass. It did not bounce. It ground forward at a maximum width of 100 yards, an entire football field of concentrated 125-mile-per-hour destruction moving directly into the southern residential and commercial districts of Ottawa. At 125 miles per hour, wind ceases to be a weather condition and becomes a blunt instrument. It is a force strong enough to generate massive negative pressure differentials inside closed structures. As the vortex passed over buildings, the external atmospheric pressure plummeted instantly. That is not just a barometer dropping. That is the physical sensation of the air itself attempting to vacuum the walls outward. Between 15th and 17th Streets, this physical reality manifested in seconds. Industrial utility poles, thick columns of treated wood anchored deeply into the earth, were cleanly snapped. The tension of power lines recoiled like severed tendons. Homes were heavily damaged. Businesses were torn open. A local motel structure was structurally gutted. The storm did not care about the municipal zoning. It only cared about the friction. 3 people were injured as the storm systematically dismantled the local grid. The subsequent damage survey conducted by the National Weather Service in Topeka confirmed the 125 miles per hour peak winds. The data was absolute, but what the survey numbers could not capture was the frightening mechanical efficiency of the event. The tornado maintained a continuous, unbroken path of destruction through a populated area for 25 minutes, and then, at 7:48 p.m., it simply lifted. The energy did not dissipate. The parent supercell merely reorganized. The atmospheric engine was still running, and Ottawa was merely its first test of structural demolition. The system was now moving east. It was preparing to weaponize an entirely different form of precipitation. As the severe weather complex pushed deeper into eastern Kansas, the atmospheric threat matrix shifted. The residents of Paola, a city just south of the Kansas City metroplex, were braced for the destructive winds that had already scarred the towns to their west. But the storm cell approaching them had reorganized its energy. It was no longer prioritizing horizontal rotation, it was prioritizing vertical suspension. The hydrometeors falling over Paola were not standard precipitation, they were not heavy rain, and they were not seasonal sleet. They were 4-inch, grapefruit-sized blocks of solid ice acting as blunt force kinetic projectiles. To understand the terrifying mechanics of giant hail, you have to look inside the engine of the supercell. Deep within the core of the thunderstorm, an updraft acts as a massive, invisible wind tunnel pointing straight up into the stratosphere. When moisture is drawn into this tunnel, it is violently thrust tens of thousands of feet into the air, forcefully crossing the atmospheric freezing line. The liquid water instantly crystallizes into a small ice pellet. Gravity pulls it back down into the warmer, moisture-rich layers below, where it collects a fresh coating of supercooled water, liquid that remains stubbornly unfrozen even below freezing temperatures. Then, the updraft catches it again. It hurls the newly coated ice back into the sub-zero altitude. It drops, it coats, it freezes. Every time this violent vertical loop occurs, the ice stone grows an additional, concentric layer, much like the rings of an old tree. A standard severe thunderstorm might cycle a hailstone 3 or 4 times, creating ice the size of a marble or a quarter. Those stones are a nuisance. They dent aluminum siding and crack older windshields. But the supercell parked over Paola was not standard. The updraft within this specific mesocyclone was operating at an extreme structural maximum. In order to keep a heavy piece of ice from falling to the earth, the upward force of the wind must exactly match the downward pull of gravity. To suspend a 1-inch hailstone requires an updraft blowing vertically at roughly 50 miles per hour. To suspend a massive 4-inch block of solid ice, the atmospheric wind tunnel must be screaming upward at sustained velocities exceeding 100 miles per hour. That is not a breeze. That is an invisible freight train running vertically into the sky. For nearly 20 minutes, the supercell over Paola maintained these impossible vertical velocities, allowing thousands of icy projectiles to grow to anomalous, catastrophic dimensions. The atmosphere held them aloft until their sheer physical mass simply overwhelmed the structural limits of the updraft. The wind could no longer carry the weight. Gravity won the equation. When a 4-inch hailstone falls to Earth, it does not drift. It drops at a terminal velocity approaching 100 miles per hour. As this barrage of grapefruit-sized ice impacted Paola, the effects were immediate and physically devastating. Residential roofs were not simply battered. The asphalt shingles and structural plywood decking were physically pulverized by the kinetic impacts. Vehicle safety glass was completely shattered, instantly exposing interiors to the deluge. The sound of the bombardment was absolute, a relentless acoustic trauma mirroring the structural destruction outside. The atmosphere was proving a sobering reality. It did not need a localized tornado to dismantle a town. It just needed gravity, a freezing line, and enough raw vertical kinetic power to hold water in the sky until it became a weapon. The visual of a grapefruit-sized block of ice falling from the sky is inherently terrifying, but the invisible mechanism required to build it is a marvel of brute atmospheric force. To understand how a 4-inch hydrometeor physically exists, one must strip away the visual chaos of the storm and look strictly at the fluid dynamics operating within the supercell's core. Within the updraft vault, the primary vertical wind tunnel of the thunderstorm, a growing hailstone is locked in a mathematical stalemate. This is not an abstract concept. This is the exact structural requirement for atmospheric levitation. In this formula, Vt represents the terminal velocity, the exact speed the upward wind must maintain to keep the ice from falling. The variable m is the mass of the object. A standard 1-inch hailstone weighs a fraction of an ounce. A 4-inch hailstone, tightly packed with dense, supercooled water that is frozen solid, weighs nearly 1.5 pounds. It is functionally a rock. The variable g represents gravity, an unrelenting downward pull. Against it, the atmosphere must utilize ρ, the density of the ambient air, and a, the cross-sectional area of the stone. Here is the terrifying reality of that equation. As the supercell forces the hailstone higher into the stratosphere, often exceeding 30,000 feet, the air density, ρ, drops significantly. The atmosphere becomes physically thinner. There is mathematically less air mass to push against the ice. To compensate for this thinning air and maintain suspension, the updraft velocity must radically increase. It must blow harder, faster, and more violently just to hold the stone in place. Finally, there is CD, the aerodynamic drag coefficient. Water freezing at these extreme altitudes does not form perfectly smooth spheres. The ice becomes lobed, jagged, and aggressively spiked. This irregular, chaotic geometry alters the friction profile. It makes the stone mathematically harder to hold aloft. When you input the mass of a 1.5-pound block of jagged ice into this equation, accounting for the thin air at 30,000 feet, the required updraft speed, Vt, crosses a staggering threshold. It demands a sustained vertical wind current of approximately 110 miles per hour. That velocity is structurally identical to a Category 2 hurricane blowing straight up into the stratosphere. The supercell parked over the Kansas border maintained this localized, invisible vertical hurricane for tens of minutes. It balanced the equation perfectly. It held millions of pounds of solid ice suspended in the upper atmosphere through sheer, uninterrupted kinetic force. But an atmospheric engine cannot burn indefinitely. Eventually, the thermal fuel at the surface is consumed. The updraft slightly weakens. The wind velocity drops from 110 miles per hour to 90. The equation fails. Gravity takes over. When a mass of that size breaks the updraft threshold, it does not float. It does not glide. It plummets. It accelerates downward until it strikes the Earth at that exact same terminal velocity. The resulting impact is the blunt force physical transfer of all that stored kinetic energy directly into the roofs, vehicles, and infrastructure below. By the late hours of April 13, the localized thermodynamic fuel over the central plains began to exhaust itself. In a standard meteorological sequence, this is the phase where storms typically decay. The atmosphere stabilizes, the threat diminishes. But this system did not decay. It actively reorganized. Instead of dissipating as it exited the plains, the storm complex underwent a fundamental structural transformation. It transitioned its kinetic geometry. It abandoned the precision of vertical rotation and embraced the brute efficiency of horizontal force. To understand this shift, you have to look at the exhaust system of a thunderstorm. As the discrete supercells, the isolated engines that produced the Ottawa tornado and the Paola hail, matured, they dropped massive, continuous quantities of precipitation. When thousands of tons of rain and hail fall through the atmosphere, they drag an enormous volume of freezing upper-level air down to the surface with them. This is known as a rear flank downdraft. When this dense, heavy air violently strikes the Earth, it has nowhere to go but outward. It acts as a fluid wedge, spreading rapidly across the terrain. Meteorologists call this expanding boundary a cold pool. You can think of a cold pool simply as a massive, invisible snowplow. When multiple supercells operate in close proximity, their individual cold pools inevitably collide. They do not cancel each other out, they fuse. They lock together to create a singular, unified boundary of dense air that can stretch for hundreds of miles. As this solid wall of cold air surges forward, it acts as a mechanical wedge, violently forcing the warmer, humid air in its path upward. That forced upward motion continuously feeds new moisture into the storm. The discrete cells merged, the localized updrafts fused, the geometry changed. The system officially became a mesoscale convective system, or MCS. The localized threat of a spinning vortex was immediately replaced by an advancing solid wall of straight-line winds. A tornado operates like an atmospheric drill bit, damaging a highly specific, narrow path. An MCS operates like a bulldozer, scraping a continuous path of destruction across multiple state lines simultaneously. The storm system was no longer reliant on the delicate balance of vertical wind shear. It no longer required a perfectly timed mid-level trough to initiate rotation. It had become a self-sustaining, forward-propagating density current. The cold air pushes the warm air up, the warm air condenses into rain, the rain pulls more cold air down, and the plow moves forward. It is a closed-loop mechanical engine. As the sun rose on April 14, this unified complex crossed the Mississippi River and tracked aggressively toward the Great Lakes. It did not matter that the deep atmospheric instability of the plains was behind it. The storm was now a blunt instrument of forward momentum. generating its own localized wind field as it marched. It was taking aim directly at the industrial heartland, carrying an entirely new type of kinetic payload. By the time the mesoscale convective system crossed the waters of Lake Michigan, it had consolidated into a massive, organized squall line. The localized chaos of the Kansas supercells was completely gone. In its place was a sweeping linear wall of dense, freezing air plowing eastward. As it approached the urban expanse of Kent County, Michigan, late on the evening of April 14, the atmospheric data stopped registering as a severe thunderstorm and began mimicking the structural profile of a tropical cyclone. At the Gerald R. Ford International Airport, located just southeast of Grand Rapids, a piece of automated meteorological equipment known as an AOSIS, an automated surface observing system, was continuously feeding telemetry back to the National Weather Service. At exactly 10:36 p.m. Eastern Daylight Time, the anemometer on that tarmac recorded a staggering physical event. The wind did not merely howl, it struck. The instrument officially registered a measured gust of 80 miles per hour. That is not a subjective estimate based on tree damage. That is not a radar approximation. That is a hard physical data point captured by an engineered sensor. To contextualize an 80 miles per hour straight-line wind, you must discard the mental image of a bad thunderstorm. On the Saffir-Simpson scale, the threshold for a Category 1 hurricane is 74 miles per hour. The velocity measured at the Grand Rapids Airport was structurally, mathematically, and physically identical to the eye wall of a landfalling hurricane walloping a landlocked tarmac hundreds of miles from the nearest ocean. When wind achieves 80 miles per hour, its kinetic energy scales exponentially. The force exerted on a structure is not directly proportional to the wind speed. It is proportional to the square of the wind speed. This means that a gust of 80 miles per hour exerts roughly 4 times the destructive, crushing physical force of a 40 miles per hour gust. It turns standard commercial signage into shrapnel. It effortlessly peels industrial roofing membranes off warehouses. It snaps the structural trunks of mature, healthy hardwood trees as if they were brittle glass. The atmosphere over Grand Rapids was proving a terrifying point about energy transfer. The squall line did not require the focused vertical rotation of a tornado to achieve catastrophic structural damage. It simply utilized an incredibly deep pool of cold, heavy air plunging violently toward the surface. When that massive block of dense air hit the ground, it forcefully spread horizontally, essentially acting as an atmospheric tidal wave rolling across western Michigan. The 80 MRI gust at the airport was just one highly calibrated measurement of a massive, continuous wall of destructive force that tore across the region. But the mechanical terror of this advancing line was not limited to the wind. The sheer volume of water being transported by this system was unprecedented for mid-April. As the wind ripped apart the canopy, an entirely different, slower, and far more lethal threat was already beginning to saturate the soil beneath it. The system was preparing to test the limits of modern hydrology. Water is heavy. That is a rudimentary fact that modern civil engineering often masks with concrete channels, spillways, and storm drains. But when atmospheric physics operates at an anomalous scale, the sheer staggering physical mass of falling water becomes an unavoidable kinetic reality. 1 inch of rain falling evenly across a single square mile of land deposits roughly 17.3 million gallons of water. That equates to more than 72,000 tons of physical mass dropping from the sky. On the night of April 14, as the massive mesoscale convective system dragged itself across Wisconsin and into Michigan, it was not dropping 1 inch of rain over a single square mile. It was dumping multiple inches of rain across a geographic footprint the size of small European countries. The atmosphere abruptly ceased acting purely as a wind engine. It transformed into an industrial-scale water conveyance system. To understand the terror of this transition, you have to look at the ground. In the upper Midwest, mid-April is a hydrologically vulnerable period. The winter snowpack has only recently melted. The deep frost has just retreated from the soil. The water table is naturally pushed to its seasonal maximum. In hydrological terms, the Earth is at its saturation capacity. You can think of it as a rigid sponge that is already entirely submerged in a bucket of water. It physically cannot hold another drop. When the squall line unleashed its massive precipitation core over this waterlogged terrain, the rainfall did not absorb. It rejected, Because the water could not infiltrate the soil, it immediately became surface runoff. It obeyed the absolute laws of gravity, rushing downward over the saturated earth, aggressively seeking the lowest possible elevation. Billions of gallons of water funneled instantly into the creek beds, the tributaries, and the primary river arteries of Wisconsin and northern Michigan. The rain fell not in measurable inches, but in sheer volumetric tonnage. This is where the threat profile completely altered. A tornado is a violent, fast-moving, localized crisis. It hits, it destroys, and it is gone in minutes. Hydrological overload is a slow-motion structural strangulation. As this unimaginable volume of water entered the river systems, it began to test the fundamental engineering of the region. Water is an incompressible fluid. It does not shrink. It does not yield. It simply accumulates. When it is forced into a confined space, like a natural river channel or a man-made reservoir behind a dam, it exerts massive, continuous hydrostatic pressure against everything holding it back. The rivers did not merely rise, they structurally bulged. The current accelerated, carrying ripped-out trees, submerged vehicles, and thousands of tons of sediment, turning the water into a heavy, abrasive battering ram. The entire hydrological network of the region was abruptly forced to process an amount of kinetic energy it was never mathematically designed to withstand. The infrastructure was built on historical baselines. It was built for the reliable, predictable weather patterns of the 20th century. But the atmosphere currently stalled over the Great Lakes was operating on a terrifying new set of rules, and the first concrete signs of catastrophic failure were about to manifest. An earthen levee is a monument to a fundamental human arrogance, the belief that compacted dirt can permanently negotiate with gravity and water. Modern hydrological infrastructure in the upper Midwest was engineered using the historical weather baselines of the 20th century. It was built to withstand the statistical probabilities of 50-year and 100-year flood events. But the atmosphere that stalled over Michigan on the afternoon of April 14 was no longer operating on those outdated meteorological curves. The mathematics of the levee simply expired. To understand how a levee fails, you must understand hydrostatic pressure. Hydrostatic pressure is not an abstract engineering concept. It is the physical, crushing weight of standing water actively leaning against a barrier. When water sits behind an earthen wall, it does not just press against the surface. It actively searches for a flaw. It probes the microscopic air pockets and organic seams hidden deep within the compacted soil. When the mesoscale convective system unleashed its unprecedented volumetric payload across northern Michigan, the tributaries feeding the Cheboygan River basin instantly overwhelmed their banks. Just outside the city limits, near the U.S. Route 23 shoreline, the Little Black River watershed absorbed an unmanageable shockload of runoff. The water rapidly filled the natural floodplains and slammed directly into the local levee system. The earth held for a time, but as the water continued to stack vertically, the hydrostatic pressure increased exponentially. This triggers a terrifying invisible mechanism known to civil engineers as piping. Piping occurs when the sheer force of the water injects moisture directly through the structural core of the levee. It finds a tiny microscopic weak point, perhaps a decayed root system or a loose seam of gravel, and forcefully pushes water through it. As the water travels, it carries away single grains of dirt, then pebbles, then clumps of clay. It acts as an internal, high-pressure drill, hollowing out the levee from the inside out, turning solid load-bearing earth into a frictionless liquid slurry. You do not see piping happening, you only see the result. On Tuesday afternoon, the internal architecture of the levee protecting the low-lying areas near the Cheboygan River fundamentally collapsed. The compacted dirt yielded, the river breached. When a levee gives way, the resulting inundation does not trickle, it sweeps. The pent-up hydrostatic pressure releases all at once, sending a heavy, debris-filled wall of cold water rushing across the terrain at a velocity that can sweep a vehicle cleanly off its axles. The water moved aggressively south toward Lincoln Street and Levering Road, weaponizing the geography against the residents. The Cheboygan County Office of Emergency Management was forced to issue an immediate, hard evacuation order. The directive to the public was grim, sobering, and utterly stripped of any bureaucratic softening. Residents were told to drop everything, move south of the city, and tie a towel or a piece of fabric to their exterior door handles. This was not a suggestion. It was a structural triage protocol. The towels were visual signals for first responders and rescue boats, a rudimentary code to indicate that a home had already been emptied before the water swallowed the first floor. The breach of the Little Black River levee was a localized tragedy, but it represented a much larger, systemic terror. The structural parameters of the 20th century were actively buckling under the sheer volumetric weight of a 21st century atmosphere. And while the Earth gave way in Sheboygan County, an even more terrifying hydrological crisis was simultaneously developing to the southwest, where a concrete dam was reaching its absolute physical limit. A levee is compacted earth, highly susceptible to the invisible drilling of localized water flow. Concrete, however, carries a profound psychological weight. We trust concrete. We anchor it deeply into bedrock. We reinforce it with woven steel gridwork, and we operate under the collective assumption that it is absolute. The imminent failure of the Balsam Row Road Dam in Shawano County, Wisconsin, aggressively stripped away that illusion. It proved a terrifying structural reality. Concrete is not invincible. It is merely a physical calculation. The Balsam Row Road Dam sits on the Wolf River, a primary hydrological artery cutting through northeast Wisconsin. In standard seasonal conditions, the dam functions as a deliberate mechanical regulator. It controls the flow, but as the unprecedented runoff from the mesoscale convective system violently funneled into the Wolf River Basin, the dam ceased to be a management tool. It became a barricade under siege. The physics operating against the structure during a flood event are defined by the hydrostatic pressure equation, P to brush AR. In this formula, the pressure, P, exerted on the barrier is the product of the fluid's density, Ra, the acceleration of gravity, G, and the fluid's vertical depths, H. The terror of this equation lies in the H. The horizontal expanse of the river upstream does not dictate the pressure. The vertical depth does. As billions of gallons of extreme runoff stacked up behind the Balsam Row Road Dam, the water level climbed higher and higher up the concrete face. With every inch the water rose, the crushing outward force pressing against the absolute bottom of the dam escalated exponentially. The concrete was no longer just holding back the surface water. It was bearing the cumulative, staggering weight of a deeply stacked vertical column. By the morning of April 15, the water was no longer merely pressing against the upstream face. It was physically engulfing the structure. The river surged over its normal operating boundaries and began to cover the concrete platform of the dam itself. When water overtops a structure not specifically engineered for continuous cresting, it triggers a catastrophic mechanical threat known as scour. Scour is hydrological erosion weaponized. As the immense volume of water cascades over the top of the dam and slams into the riverbed below, it acts as an industrial grinder. It violently excavates the sediment, rock, and earth directly at the downstream base of the concrete foundation. It literally digs the ground out from under the structure. If the scour reaches deep enough, the concrete anchors lose their grip. The hydrostatic pressure pushing from behind remains constant, but the friction holding the dam in place vanishes. The dam does not simply leak. It violently slides forward and shatters. The data was rapidly approaching this mathematical breaking point. The National Weather Service in Green Bay recognized the structural geometry of the crisis and triggered a deeply unsettling alert. They issued a flash flood watch explicitly for the potential imminent failure of the Balsam Row Road Dam. The Shawano County Sheriff's Office urged downstream residents to prepare for immediate, rapid evacuation. Emergency management did not mince words. If the concrete failed, a towering wall of heavy, debris-filled water would violently flush through the lower Wolf River Basin, inundating low-lying areas and surrounding rural communities with zero warning. The response at the site was a frantic, physical battle against fluid dynamics. Heavy equipment crews were rushed to the banks. They hastily constructed massive earthen berms on both sides of the dam to artificially raise the barrier height and force the water back into the primary channel. Simultaneously, crews worked desperately to drag massive, waterlogged trees and shattered debris out of the raging current to keep the dam's gates from choking. They were not fixing the weather. They were merely trying to stall the math. Through sheer, desperate mechanical intervention, the berms held. The debris was cleared. The water level crested by a margin measured in inches, narrowly avoiding a complete structural shear. The Balsam Row Road Dam survived the siege, but it stood as a horrifying proof of concept. The atmosphere possessed the physical capacity, through sheer volumetric payload, to simply crush our civil engineering under the weight of the sky. The flooding was catastrophic, but the atmospheric engine driving it was not finished. It was merely taking a breath. To the residents of the plains and the upper Midwest, the morning of April 16 felt like an atmospheric truce. The violent, rain-wrapped supercells were gone. The localized hurricanes of straight-line wind had exited into Canada. The sun emerged, warming the storm-battered pavement. But this tranquility was fundamentally deceptive. The atmosphere was not recovering. It was reloading. Following a massive, multi-day severe weather sequence, the lower atmosphere is typically exhausted. The thermal energy is spent. The moisture is scoured out by the advancing cold fronts, leaving behind cool, stable, and sterile air. But the architectural geometry of the jet stream had not changed. A massive high-pressure system parked over the eastern seaboard acted as an unyielding atmospheric wall, forcing a continuous low-level wind current to draw directly out of the Gulf of Mexico. The moisture was not scoured. It was aggressively returning. By midday on April 16, surface dew points across Oklahoma, Kansas, and Missouri were rapidly surging back into the mid-60s. A dew point in the mid-60s is not merely humid, it is the exact threshold where the air feels physically heavy, carrying the dense latent heat required to build massive convective updrafts. The surface was becoming a saturated powder keg, but the skies remained eerily blue. This terrifying calm was enforced by a meteorological phenomenon known as an elevated mixed layer, or EML. An EML is a thick slab of incredibly dry, hot air generated over the high elevations of the desert southwest and the Mexican plateau. Strong, high-altitude westerly winds sheared this boiling desert air off the mountains and dragged it directly over the central plains. Because this air is so abnormally hot, it creates a severe temperature inversion, a rigid, invisible lid placed a few thousand feet above the suffocating moisture at the ground. Meteorologists call this the cap. It is a mechanical suppressor. The cap forcefully prevents the saturated surface air from rising, completely shutting down the formation of harmless, energy-burning rain showers. Instead of slowly releasing the tension, the atmosphere is forced to hoard it. As the April sun baked the ground, the trapped latent heat magnified exponentially. The convective available potential energy, the raw mathematical fuel for supercell thunderstorms, began to climb back into the extreme tiers, slowly exceeding 3,000 joules per kilogram beneath the cloudless skies. The atmosphere was winding the spring tighter than it had been on April 13. The radar was entirely blank, but the telemetric data was screaming. The surface was locked, the humidity was surging, the cap was holding, the central United States was entirely submerged in a state of extreme, suspended volatility. It was a false equilibrium, a temporary pause dictated strictly by the physics of the elevated mixed layer. The system did not need days to prepare for another structural assault. It only needed a mechanical trigger strong enough to punch through the desert air. And in the upper atmosphere, descending rapidly from the Great Basin, that exact trigger was already in motion. The atmosphere does not randomly combust. To break a severe localized thermal cap, the structural lid of the elevated mixed layer suppressing the Great Plains, requires a kinetic trigger of immense hemispheric scale. On the morning of April 16, that trigger was not building over the humid, saturated soils of the Midwest. It was ejecting out of the high, arid elevations of the Great Basin. Meteorologists track this mechanism as a shortwave trough. To understand a shortwave trough, you must visualize the jet stream not as a gentle, meandering river of high-altitude wind, but as a violent, atmospheric whip. The jet stream flows in massive continental waves across the northern hemisphere. A shortwave trough is a concentrated, rapidly moving kink deeply embedded within that larger atmospheric flow. As this sharp, cyclonic kink tears through the upper troposphere at speeds exceeding 120 miles per hour, it carries a localized pocket of extreme rotational energy known in fluid dynamics as positive vorticity advection. Positive vorticity advection is a technical academic term for an invisible atmospheric plow. As the high-altitude air enters the base of this trough, it is forcefully squeezed together and spun counterclockwise. However, as the jet stream exits the trough on its eastern edge, the wind field abruptly and violently spreads out. This rapid, horizontal spreading at 30,000 feet creates an instantaneous localized vacuum near the edge of the stratosphere. The absolute physics of the atmosphere dictate that a vacuum cannot exist. To balance the mathematical equation, Immense volumes of air from the lower levels of the atmosphere must be pulled vertically to replace the missing mass aloft. The sky inhales. This forced upward motion acts as a massive, continuous suction tube dragging across the terrain. When this specific, deeply carved shortwave trough ejected over the Rocky Mountains and arrived above the Central Plains, it encountered the boiling, violently capped energy station below. The trough did not gently erode the elevated mixed layer. It mechanically ripped it open. The sheer vertical suction of the positive vorticity advection overpowered the thermal suppression of the cap, grabbing the volatile, moisture-loaded air at the surface and violently scooping it upward into the freezing layers of the troposphere. The lid vanished, the equilibrium shattered, the engine engaged. By the early afternoon, the physical manifestation of this upper-level trigger was structurally undeniable. The completely blank radar screens of the morning were abruptly contaminated with explosive vertical towers of boiling cumulus clouds, rising at velocities that defied standard seasonal convection. The shortwave trough had successfully transferred its upper-level kinetic energy directly down to the surface, translating invisible high-altitude wind physics into the rapid genesis of a massive, highly organized severe weather outbreak. The atmosphere had systematically loaded the thermodynamic chamber, and the Great Basin Trough had definitively pulled the trigger. But to maximize the geographic scale of the destruction, this newly liberated thermal energy still needed something heavy to collide with at the surface. The trigger had been pulled in the upper atmosphere. But a shortwave trough operating at 30,000 feet is only half of the structural equation required for a multi-state disaster. To generate a widespread severe weather outbreak, that high-altitude exhaust system must perfectly align with a massive mechanical forcing mechanism at the surface. On the afternoon of April 17, that mechanism arrived. It was a surging wall of dense, freezing air marching steadily eastward from the northern plains. In meteorological terms, a cold front is often oversimplified as a sudden drop in temperature. That is a dangerous underestimation. A cold front is fundamentally a density boundary. It is not a breeze. It is a physical advancing collision of atmospheric masses with violently differing molecular weights. To understand the terror of this collision, you must look at the air mass waiting ahead of it. The central United States was trapped in a hypersaturated warm sector. Surface dew points had climbed aggressively, locking in the mid-60s across a massive geographic footprint. A dew point is not relative humidity. It is a strict, absolute measure of physical water vapor suspended in the air. When a dew point reaches 65 degrees Fahrenheit, the air ceases to be merely humid. It becomes physically heavy. It becomes volatile. It becomes fuel. This saturated environment contained trillions of megajoules of latent thermal energy. It was sweltering, pressurized, and deeply unstable. But because of the lingering thermal cap, it was held violently in place. It needed a wedge to force it upward. The advancing cold front did not mix with this sweltering moisture. Cold air is fundamentally denser than warm air. Its molecules are packed tightly together, making it structurally heavier and mathematically unyielding. As this massive block of freezing air plowed across the plains, it acted exactly like the steel blade of an industrial snowplow. It physically forced itself directly underneath the hypersaturated warm sector. The warm air had nowhere to go but up. When the heavy wedge of the cold front undercut the mid-60s dew points, the resulting vertical lift was explosive. The humid air was abruptly thrust tens of thousands of feet into the freezing upper troposphere. It was pushed directly into the violent waiting suction of the Great Basin Trough operating overhead. The two mechanisms, the surface plow and the high-altitude vacuum, synchronized with perfect, terrifying efficiency. The forced ascent was immediate, the ascent was vertical. The ascent was catastrophic. The localized, deceptive calm of the previous 24 hours was instantly obliterated. Along the leading edge of the density boundary, the sky darkened as massive, boiling towers of cumulus clouds erupted into the stratosphere. The boundary line ignited, transforming from a quiet collision of invisible air masses into a continuous, volatile chain of rapid supercell genesis. The atmospheric engine had successfully engaged. The atmosphere was no longer loading. It was firing. Deep within the fortified facility of the Storm Prediction Center in Norman, Oklahoma, meteorologists do not deal in panic. They deal in probabilities. Their primary tool for communicating threat to the public is the convective outlook, a rigid 5-tier scale designed to categorize atmospheric violence. For most of the spring season, the map is painted in the lower, conditional tiers, marginal, slight, and enhanced. These categories indicate that severe weather is possible, provided certain localized triggers align. But on the morning of April 17, the meteorologists on duty reviewed the incoming telemetry from the cold front collision. The thermodynamic and kinematic data did not align with a conditional threat. The data demanded a categorical escalation. The Storm Prediction Center outlined a massive corridor, stretching from northwest Oklahoma straight through the heart of Kansas and extending into west-central Missouri. They painted it in red. They issued a moderate risk. To the general public, the word moderate implies something average, something manageable. In the strict, unyielding lexicon of atmospheric science, a moderate risk is a level 4 out of 5. It is a deeply sobering categorization. It is not a precaution. It is not a localized forecast. It is a statistical guarantee of consequential, life-threatening weather across a massive population center. The SPC does not issue a moderate risk lightly. Statistically, it is utilized on fewer than 20 days out of the entire calendar year. When it is deployed, the underlying algorithms have detected the exact atmospheric architecture required for widespread, long-lived, and intensely severe storms. It explicitly indicates that the capping inversion is mathematically guaranteed to break. It means the rotational wind shear is structurally locked into place. It signifies an environment definitively capable of producing violent tornadoes, destructive straight-line wind walls, and localized hail bombardments simultaneously. The scientists in Norman stripped away the hedging. They removed the comforting qualifiers of might be or could potentially. The atmosphere had bypassed localized instability and achieved a state of systemic, regional capability. The physical ingredients for a major convective outbreak were no longer theoretical projections on a computer model. They were measurable realities anchored over the Midwest. The target area was officially marked, but the moderate risk was only the probabilistic forecast. The actual, imminent trigger of the event required an entirely different, legally binding alert. A staggering geographical footprint was about to be placed under a singular, terrifying warning umbrella. The Storm Prediction Center does not draw lines on a map arbitrarily. When they define a threat area, they are drafting a strict mathematical boundary of atmospheric capability. At 12:40 p.m. Central Daylight Time on April 17, as the freezing cold front aggressively engaged the hypersaturated warm sector, the center issued a mandate. They activated Tornado Watch number 129. A standard severe weather watch typically covers a handful of counties. It is localized, it is regional, it is manageable. Watchbox 129 was fundamentally different. It was a geographical monster. The designated polygon extended 110 miles north and south of a precise geometric axis, drawn from just northwest of Des Moines, Iowa, all the way to the eastern outskirts of Madison, Wisconsin. It did not respect municipal or state boundaries. It swallowed them. The sheer, staggering scale of the watch area simultaneously encapsulated portions of 5 separate states: Iowa, Illinois, Minnesota, Missouri, and Wisconsin. It turned the entire upper Midwest into a singular unified threat zone. When the National Weather Service issues a tornado watch of this magnitude, it is communicating a specific structural reality to emergency managers. It means the localized ingredients for catastrophic weather, the sweltering surface heat, the deep moisture, and the violent rotational wind shear are not just present in a single pocket. They are distributed uniformly across hundreds of miles. Any storm cell that initiates anywhere within that massive polygon will instantly possess the mechanical fuel to become violent. The text of the alert was explicitly stripped of bureaucratic comfort. It formally forecast the development of widespread, giant hail, specifically targeting the 3.5-inch diameter threshold. It warned of sweeping, straight-line wind gusts reaching 70 miles per hour. But most terrifyingly, the primary hazard listed was not just the generalized probability of funnel clouds. The watch explicitly noted the environment was structurally primed for a couple of intense tornadoes. In the sterile, precise language of meteorology, intense is not a descriptive adjective. It is a rigorous categorization. It means the atmospheric physics mathematically support the genesis of long-track EF3, EF4, or EF5 vortices. It means the rotational wind fields will exceed standard building code tolerances. It means the storms are capable of erasing foundations For more than 7 hours, until the watch officially expired at 8 p.m., millions of residents across 5 states were locked under the exact same atmospheric gun. The radar was no longer a tool for long-range seasonal planning. It was a tactical display of imminent physical threats. The massive footprint of Box 129 proved that the atmosphere was not planning a skirmish. It was orchestrating a regional siege, and the initial, localized detonations were already beginning to materialize on radar. When the initial radar returns began to paint across the screens inside Watchbox 129 on the afternoon of April 17, they did not appear as a solid, intimidating line of red. They appeared as tiny, isolated dots separated by vast expanses of clear air. To the untrained eye, this scattered presentation might suggest a disorganized, manageable weather event. In the rigid mechanics of atmospheric physics, it is the most dangerous optical illusion nature can project. These isolated dots were discrete supercells. A discrete supercell is a thunderstorm that operates entirely alone. It is a singular, independent, and intensely violent thermodynamic engine. To understand why isolation makes a storm exponentially more lethal, you must look at how a thunderstorm breathes. A supercell requires a massive, continuous intake of hot, hypersaturated surface air to survive. This intake is called the inflow. You can picture the storm as an industrial vacuum, aggressively pulling the sticky 65-degree dew point air from miles around directly into its vertical updraft. When storms initiate too close together, their physics inevitably clash. They compete for the same moisture, they disrupt each other's wind shear, they choke on their own cold exhaust. But when a capping inversion breaks cleanly, allowing storms to fire 20, 30, or 40 miles apart, the competition vanishes. The supercells that ignited across the moderate risk zone that afternoon had exclusive, uncontested access to the atmosphere's deep thermal reservoir. Because they were widely spaced, there were no neighboring cold pools to cut off their warm air supply. Each individual storm was surrounded by a 360-degree radius of untouched, highly pressurized kinetic fuel. They did not share the energy, they gorged on it. Without interference, these independent engines were free to utilize the extreme vertical wind shear perfectly. The low-level jet stream grabbed the uncontested inflow and violently spun it. The updrafts began to rotate. The invisible horizontal rolling tubes of air were smoothly tilted vertical, anchoring deeply into the lower troposphere. The structure was pristine. The mechanics were uninhibited. The rotation was absolute. Operating as independent entities, these localized cells began dropping their pressure cores and generating the initial wave of hazards. They were perfectly calibrated to construct strong EF2 to EF3 tornadoes and unleash massive vertical hail cores without the disorganized chaos of a squall line. The atmosphere was not yet building a sweeping wall of destruction. It was building individual, highly calibrated weapons. But this phase of isolated precision is mechanically unsustainable. As the afternoon wore on and the thermal energy peaked, the individual engines began to expand their footprints, preparing to abandon their isolation and fuse. The sheer thermodynamic cost of building giant hail is staggering. When a thunderstorm constructs a massive block of ice, it fundamentally depletes the kinetic energy of its immediate environment. The updraft consumes the available heat. The downdraft scours the localized moisture. In standard meteorological events, a supercell fires its primary volley and then slowly suffocates on its own cold exhaust. But as the afternoon of April 17 unfolded across the Mississippi Valley, the atmosphere aggressively rejected this standard sequence. It did not suffocate. It efficiently reloaded. The discrete supercells initiating along the collision zone between the Great Basin Trough and the advancing cold front found themselves positioned over a deeply carved topographic basin. The Mississippi Valley is not merely a geographic feature, it is an atmospheric conduit. It acts as a massive low-elevation trench that naturally funnels the thickest, heaviest moisture directly northward from the warm waters of the Gulf of Mexico. When the isolated supercells drifted over this terrain, they encountered an environment that was actively replenishing its own fuel supply faster than the storms could consume it. The result was a terrifying, systematic duplication of the extreme anomaly that had battered the plains days prior. Deep inside the storm cores, the radar reflectivity data, the precise measure of how much physical mass is suspended in the cloud, began to max out the color scale. The digital readouts turned from deep red to a stark, ominous white. This specific radar signature, known to meteorologists as a three-body scatter spike, occurs only when the density of ice within the storm is so immense that the radar beam physically bounces off the hail core, hits the ground, bounces back to the hail, and then finally returns to the dish. It is an optical artifact, but it represents a massive physical reality. The supercells over the Mississippi Valley were once again suspending millions of pounds of solid water in the freezing upper troposphere. The updrafts were screaming vertically at speeds exceeding 90 miles per hour, forcefully holding the ice aloft until it reached 3.5 inches in diameter. To produce hail of this magnitude once in a severe weather sequence is a localized disaster. To produce it a second time, across an entirely different geographic footprint hundreds of miles away, is a display of terrifying structural capability. When these 3.5-inch projectiles finally overcame the vertical wind shear and plummeted to the earth, they arrived at terminal velocities approaching 100 miles per hour. The physics of the impact scale exponentially with size. A standard 1-inch hailstone strikes a roof with roughly 1 foot-pound of kinetic energy. It is an annoyance. A 3.5-inch block of solid ice falling at highway speeds strikes the earth with nearly 200 foot-pounds of localized kinetic force. That is not precipitation. That is a ballistic impact. Roofs were systematically pulverized. Vehicle safety glass was shattered instantly, exposing interiors to the torrential deluge. Livestock caught in open pastures were subjected to a lethal, blunt-force bombardment. The atmosphere was proving a sobering mathematical reality to the residents below. The terror of the Central Plains was not a geographic fluke. The physics were perfectly transferable. The engine was completely portable. The destruction was systematically replicated. The atmospheric machinery had successfully moved its primary hail factory into the industrial and agricultural heart of the Mississippi Valley, and it was operating at absolute peak efficiency. But as the sun began to lower toward the western horizon, the thermal dynamics of the region began to subtly shift. The isolated supercell engines were generating too much cold exhaust, and they were rapidly running out of individual space. The independence of a discrete supercell is its greatest weapon, but it is fundamentally limited by its own thermodynamic waste. Thunderstorms do not just consume heat, they expel cold. As the late afternoon of April 17 transitioned into early evening, the isolated atmospheric engines tearing across the Mississippi Valley began to violently choke on their own exhaust. To understand this structural collapse, you must examine the atmospheric exit wound. Inside a mature supercell, the intense precipitation core, the billions of gallons of rain and suspended hail, acts as a heavy, frictional drag on the surrounding air. As this frozen payload plummets toward the Earth, it violently pulls freezing air from the upper troposphere down to the surface with it. Meteorologists define this deeply concentrated plunge as a downdraft. When this dense, freezing column of air impacts the ground, it cannot penetrate the soil. It forcefully spreads outward in all directions, rolling across the terrain as a heavy, localized density current. This boundary is the cold pool. You can visualize it as a massive, invisible volume of heavy water dropped onto a flat surface. For the first few hours of the outbreak, the supercells were spaced far enough apart that their expanding cold pools never touched. The engines remained isolated, the inflow remained pure. But as the atmospheric forcing increased along the advancing cold front, more and more storms rapidly initiated within the moderate risk zone. The geographic gaps between the storm cores aggressively shrank. The isolated waves of cold air expanded outward, rapidly closing the remaining distance. Then they collided. They did not bounce off one another. They did not dissipate. They fused. The individual cold pools structurally interlocked, instantly merging their localized density currents into a singular, unbroken boundary of freezing air spanning hundreds of miles. The atmospheric physics completely dictated the next phase. When a continuous wall of heavy air plows forward, it fundamentally alters how the surrounding atmosphere behaves. The storm system stops acting like a series of isolated vacuum tubes. It begins acting like a continental snowplow. The hypersaturated volatile air waiting ahead of the storm no longer had the luxury of spiraling upward into discrete, rotating mesocyclones. It was abruptly and uniformly shoved straight up by the advancing wedge of the merged cold pool. The physical forcing was no longer localized. It was strictly linear. This linear forcing triggered a terrifying architectural transition in the sky. the individual updrafts of the once isolated supercells physically connected. They zipped together across the horizon, fusing from discrete vertical columns into a single, massive, organized convective line of terror. The thermodynamic energy of 50 separate storms was consolidated into one unbroken structure. The mesocyclones weakened, the precise rotation unspooled, the giant hail began to diminish. This was not a decay, it was a calculated, mechanical redistribution of kinetic energy. The storm system was actively converting its vertical rotational power directly into forward horizontal momentum. The atmosphere was explicitly finished building surgical, localized tornadoes. It was now constructing an atmospheric battering ram. When the individual supercells zipped together across the radar screen, the digital display fundamentally morphed. It stopped showing isolated spinning cores. It began to paint a solid, unbroken line of deep red. And then, the center of that massive line began to aggressively bulge forward. Meteorologists refer to this structural deformation as a bow echo. To the untrained eye, it looks like a backward letter C sweeping across the map. To a fluid dynamicist, it is the physical signature of an atmosphere weaponizing momentum. To understand how a squall line bows, you must examine the thermodynamics occurring directly behind the storm. As the unified convective line dumped billions of gallons of rain, the intense evaporation cooled the air in the storm's wake. This massive pool of cold, dense air sank to the surface, creating a localized high-pressure zone. Simultaneously, the warm updrafts at the front of the storm continued to rise, creating a localized low-pressure zone aloft. This extreme pressure gradient triggered a terrifying atmospheric mechanism known as a rear inflow jet. The storm system essentially generated its own private mid-level jet stream. It actively sucked a horizontal channel of dense, dry air from outside the system directly into the back of the thunderstorm line. But this jet did not flow parallel to the ground. It was angled downward. The rear inflow jet plummeted from the mid-levels of the troposphere, accelerating toward the surface like water rushing down a massive, invisible chute. When this freezing, heavy jet violently struck the ground just behind the leading edge of the storm, it had nowhere to go but forward. It acted as an atmospheric bulldozer. It forcefully shoved the center of the convective line ahead of its northern and southern edges, physically bending the storm into its signature bow. The wind velocities trapped inside this advancing bulge were staggering. As the bow echo tore across the Mississippi Valley and the Great Lakes, the anemometers did not record brief, chaotic gusts. They measured a sustained, sweeping wall of straight-line wind, pushing 60, 70, and peaking at 90 miles per hour. At 90 miles per hour, wind is a blunt instrument. It exerts exponential crushing pressure on the built environment. It peels commercial roofing. It snaps industrial utility poles. It strips the landscape clean. At the northern and southern extremes of this massive bow, the sheer friction of the advancing wind wall dragged against the surrounding stagnant air. This friction created massive, counter-rotating eddies known as bookend vortices. The northern vortex spun cyclonically. The southern vortex spun anticyclonically. They functioned as immense atmospheric gears, physically anchoring the ends of the storm and funneling even more kinetic speed directly into the center of the bow. The threat profile was completely rewritten. A discrete tornado is a drill. It destroys an isolated, narrow path. A bow echo is a structural shear. You cannot seek shelter by simply stepping out of the path of a funnel. You cannot sidestep a 90-mile-per-hour wind wall. It is an advancing density current, 50 miles wide, forcefully scraping the Earth as it rolls toward the horizon. The atmospheric transition was complete. The localized precision was gone, replaced by a mathematically efficient, self-sustaining engine of regional demolition. Across 5 continuous days, the atmosphere processed an estimated 2.4 trillion megajoules of kinetic energy from the plains to the Great Lakes. But the billions of dollars in structural and hydrological damage isn't the part that has forecasters alarmed. It is the invisible, planetary-scale architecture that allowed this localized devastation to physically repeat itself with absolute mechanical precision. Are we looking at a statistical atmospheric glitch or the activation of a permanently locked-in pattern? To understand the horror of a 5-day meteorological siege, you must pull back from the localized radar and look at the planetary scale. The mid-latitude weather of the Earth is dictated by Rossby waves. Rossby waves are massive, slow-moving, high-altitude rivers of wind that undulate across the hemisphere. They are the grand steering mechanisms of the atmosphere. Under normal historical baselines, these waves flow steadily from west to east. They bring a storm, they scour the moisture, and they move on. The system breathes. But during the April sequence, the wave did not move. It stalled. Fluid dynamicists refer to this as atmospheric blocking. The jet stream essentially acts as a massive high-speed traffic jam, causing deep atmospheric troughs to become physically anchored over the exact same geographic coordinates for days. This blocking mechanism locked the Great Basin Trough, the continuous upper-level vacuum, directly over the central United States. It acted as a stationary trigger. It was a hammer programmed to strike the exact same anvil, day after day. But a repetitive trigger is only lethal if the weapon continuously reloads. This is where a rigid, 190-year-old law of thermodynamics enters the equation, the Clausius-Clapeyron relation. The Clausius-Clapeyron equation is not a climate model projection. It is an absolute, non-negotiable physical law that dictates exactly how much water vapor the air can hold at a given temperature. The mathematical reality is governed by an exponential curve, simplified as dt dq approximately 0.07 times q. For every single degree Celsius the atmosphere warms, its physical capacity to hold water vapor increases by roughly 7%. 7% does not sound catastrophic until you apply it to the immense volume of the Gulf of Mexico. Because the baseline temperature of the ocean and the lower atmosphere has systematically increased, the low-level jet stream is no longer transporting standard seasonal humidity. It is dredging an anomalously heavy, supersaturated payload of moisture northward. The air is not just warmer, it is physically thicker. It is loaded with a substantially higher baseline of latent heat. When you combine a stationary Rossby wave with a supercharged Clausius-Clapeyron baseline, the atmospheric friction vanishes. The system achieves a terrifying mechanical synergy. The stalled trough provides the continuous vertical suction. The warming gulf provides the mathematically expanded endless thermal fuel, and the advancing cold fronts provide the physical wedge. During those 5 days in April, the atmosphere proved it could synchronize these extreme variables flawlessly. It built violent EF3 tornadoes, levitated millions of pounds of giant hail, and unleashed sweeping bow echoes with the unyielding efficiency of an industrial assembly line. The data from the plains to the Great Lakes is unequivocal. The 3,000 joules of Cape, the 140-mile-per-hour vortices, the 80-mile-per-hour straight-line winds, the shattered levees and the overrun dams. This was not a fluke. It was not a statistical anomaly. It was a localized demonstration of a new planetary capability. The atmosphere has rewritten the baseline. The pattern is locked.